So what happened? I feel like there's some serious beef between the legendary department and the school.
but at least we didn't record my venting for 30 minutes. Okay. And we really haven't even got that far into the notes. Yep. Everyone but Nisha.
How many U's do you have? Like five?
Like 25. 25 probably.
Oh, 25.
Okay. So we've talked about this probably. An ionic bond will be a bond between a metal and a nonmetal. We have to have a loser. We have to have a gainer. Metals lose, nonmetals take. They do not share electrons. Now, this class, AP chemistry, we always find a way to bring math in, right? So there's not a, we're going to do some numerical ideas here, but you don't have to calculate math on this very often, but we're going to talk about it. All right. So when we talked last week, we talked about ionization energy. Okay, so this section is called energetics of ionic bonding. It's kind of important, but it's not super awful. As we saw in the last chapter, it takes 495 kilojoules to remove electrons from sodium. So if I have Na, okay, that's supposed to say Na, and it has its valence electron, it does, even though a metal's a loser, it still takes energy to remove it. Okay, because we're taking something negative and moving it away from something positive. So it always requires energy, and it's called the ionization energy. Now, this is not very much in the long run, but anyway, we have ionization energy, which is 495. All right, we get 349 kilojoules per mole back by giving the electron to chlorine. This is exothermic because the electron was far away and moved closer to the nucleus, and that gives off energy. That's an arrow. Yeah, there's not a lot of change. I mean, there's more than you would expect. There's 150 difference. Okay. So there's these two steps, but there's really a third step. And you don't have to do the math, you just have to understand the math. Okay. But these numbers do not explain why the reaction of sodium metal and chlorine gas to form sodium chloride is so exothermic. In fact, if you did the math a minute ago, you would have realized it's endothermic to make sodium chloride, but it definitely is not. It is an exothermic process. So the third step we're going to learn about is an important thing called lattice energies. So there must be a third piece of the puddle. Oh gosh, the puzzle. What is as yet unaccounted for is the electrostatic attraction between the newly formed sodium cation and the chloride anion. So when sodium gave its electron away, there was some energetics there. When chlorine took it, there was some energetics involved. But now they're oppositely charged and they will move towards each other and stick together. That process releases energy. This energy is called the lattice energy, and it is the energy required to completely separate a mole of a solid ionic compound into its gaseous ions. The energy associated with electrostatic interactions is governed by Coulomb's law. Okay, so I will come back. I'll talk through all that. But what we're saying is if I had a big chunk of sodium chloride, okay, and it's not drawn to scale by any means or any accuracy, but let's just pretend that this is a piece of salt. These ions are stuck together in a very solid substance. If I want to pull it apart, I have to break all these electrostatic interactions. So it would be like we're pulling apart tons of magnets. We could do it, but it would take some energy, right? So think about this, the way that nature works. If it takes energy for me to pull these things apart, then when they were formed, it must have given off energy because everything is equal but opposite. Let me say that one more time. If it makes sense that it requires energy to pull it apart, then it should hopefully make sense that it gave off energy when it was formed. Okay. That energy that is released in this formation is lattice energy. Now, we don't have to do the math once again, but we have to understand the application of the math and Coulomb's law. And this is the second time we've talked about Coulomb's law, correct? Coulomb's law says that the force of attraction or repulsion is equal to Q1, Q2 over R or D squared. It doesn't matter, radius or distance, all right, not diameter, but you'll see it written as both, where Q1 would be the charge of Na, Q2 would be the charge of Cl, and I should put plus and minus, that was poor, there you go. So the charge of Na plus, the charge of Cl minus, divided by their distance between them. Okay. So this, I've said it like 3 times. We don't ever have to calculate the force. We have to understand the force and the things that affect the force. So tell your partner at least one thing I could change that would change the answer for F. All right. So I could change the charges if I had different atoms or the distance between them if they were different sizes. Okay. So the lattice energy for NaCl, let's just pretend it's 100. Now it's not, but let's just pretend. But if I wanted to do the lattice energy for MgCl2, I don't know what it would be, but I know it would be bigger. How do I know it would be bigger? Because the charge is bigger. This is the charge of Na plus, but if it's Mg, it's now Mg plus 2. So this becomes a 2. This becomes a 1. We would calculate it between each Cl. So we wouldn't double it because we're talking about this right here. You all right with that? But we would double this because it's a plus 2. So lattice energy depends on the charge of the ions involved, and it will depend on the size of the ions involved. So let me think about, or let me ask you this. The lattice energy of KCl, tell your partner if you think it's bigger, higher or lower than 100. Fabian said the right answer, so everyone say I agree.
Aha!
Why is it less, Fabian?
Because K has a bigger like radius or distance,
Okay.
and it has the same charge as Na.
All right.
So you're dividing by distance. Everything stays the same except for distance, which is getting bigger. So you're dividing by a bigger number, making that number smaller.
There you go. So these are really, really typical test questions. You don't have to know 100 or 300 or whatever, but you have to know which one will be bigger or smaller And unfortunately, some of you didn't like it, but you also have to know why. Go ahead.
On the AP test, did we get the periodic?
Yeah, it's the same periodic table I've given you for tests, except for it's
So a lot
green.
of this concept all is just building off of like last chapter of like
Yeah, this all relates to last chapter.
I feel like each chapter always goes off of the chapter.
Yeah, chapter 5 is a little bit out of order to me, but everything else builds. Chapter 5 and chapter 19 actually go really well together, and I used to just leave 5 until 19, but you really need some of 5 throughout. So anyway, but yeah, they do build. Okay, so if you look, uh, here are some typical numbers here. Lattice energy then increases with the charge on the ions. So you'll see 1 and 1 versus 2 and 1. We went from 1030 to 2326. And it also increases with decreasing size of ions. So you'll notice cesium's really big, iodine's really big, so this energy is really small. This is an important thing. You have to be able to be, you'll be given a couple lattice energies and asked why they are the way that they are. So you would say something like magnesium chloride has a larger lattice energy because it's got a larger charge. Magnesium is twice the charge as lithium. But also still, please remember, if we have Mg, Cl, Cl, we're finding the lattice energy that is attraction between these two things. So we don't double it and double it. We have the Mg plus 2, that's why it doubles, but not because there's two separate Cls. We're finding it for one piece each time. Okay.
Won't the atom,
Try and answer these real quick. Go ahead. What?
won't the atoms like even because they're being repelled by
The other nucleus?
well the other ones of the same like magnesium will be repelled by another thing of magnesium.
Yeah, they will. And that's why they'll always have one in between them. And we get really, really nice orderly crystalline structures. So of the following pairs, which would you expect to have the highest lattice energy when they form an ionic bond? Explain your reasoning. You will have questions on the test exactly like this. Don't take the next test unless you know how to answer this question. Well, still take it, but you should know how to answer this before you sit down that day. Bennett, this affects you. It's Tom, our pole vaulter coach. Well, it was supposed to be Savannah's dad, remember?
Yeah, yeah.
But he's the one that emailed me. Let me read it. Oh, he texted me. I'm an idiot.
I love it. I miss it. Is it scary at all? I mean, when you're first learning it, but you just
But after you're already going into the air, I mean, I think it was more scary doing just high jump. Davidson can tell you why.
scary.
It's not as bad as I thought. Sorry.
Cool, cool.
That's circumcision by me.
All right. So, which one of these would have the highest lattice energy in number one? All right, this one. Why?
Smaller.
Because it's the smallest out of the three.
All right.
So the radius.
The radius is the smallest between these two atoms. I definitely want something about the radius or the distance. Okay. How about these?
Aluminum.
How come?
The charge is greater in aluminum.
It's a plus 3.
The aluminum has the highest ionic charge. We all right with that? I imagine Cronin's here because we get out in 50 seconds. Is that accurate? Okay. That was kind of a disaster day, but I vented. I feel better.
That's all that matters, Dave.
But don't,
Anything to get
so
left
help
out
me.
of work and make you feel better.
So help me if any of you, if I hear, hey, your student said you hate the English or math department, I'll kill you.
I'm gonna go tell Mumford that. Mumford, I'm tired of your department.
You can tell the math department I don't like them. They know that.
They know that.
He looks like a water star.
JC, that was probably a waste of your time. I apologize.